Today, we're going to look at a really simple change you can make in your Java code that can give you a massive performance boost, especially when you're working with files. I mean, really think about that for a second. What if the way you're handling files right now, character by single character, is the one hidden bottleneck that's just dragging your whole application down? It's a way more common problem than you'd think, but lucky for us, the fix is super elegant. And here's the thing that might surprise you. Most of the standard ways we learn to handle files in Java are, well, inefficient by default. It's not that you're doing anything wrong, it's just how the basic tools are built. But Java gives us an awesome solution, and it's called buffering. In this explainer, we're going to break down exactly how buffered streams work and how you can use them to make your file operations way faster. Okay, so let's dig into the root of the problem here. Why are those basic tools, a simple file reader or file writer, so slow, especially when the files start to get big? Well, the main culprit is that with unbuffered I/O, every time your program wants to read just one little character or write one little character, it has to go make a direct request to the operating system. It's like having to knock on the OS's door for every single piece of data. These requests are called system calls, and they are seriously expensive from a performance standpoint. Each one might involve physically accessing a hard drive or hitting the network. Now, just imagine you're trying to process a huge log file. You could be making millions, even billions of these tiny individual system calls. The overhead is just enormous. This slide has the perfect analogy for it. Unbuffered I/O is like driving to the grocery store to buy one egg, then driving back home, then driving back to the store for a cup of flour. It's completely insane. Buffered I/O, on the other hand, is like making one trip with a full shopping list. You get everything you need all at once. So much smarter. So let's talk more about that shopping list. This is the buffering solution. It's all about working smarter, not harder, when it comes to your file operations. So what even is a buffer? It's really simple. It's just a temporary holding area in your computer's fast memory, its RAM. So instead of going directly to the slow hard disk every single time, your program gets to hang out and talk to this much faster in-memory staging area. This diagram shows the new flow perfectly. The buffer acts as the super efficient middleman. It moves big chunks of data between the slow file system and your program. So your program mostly just talks to the buffer, which cuts down on all those expensive direct chats with the operating system. Okay, let's see how this actually looks in practice. First up, let's tackle reading files efficiently. And for this, we're going to use our new best friend, the buffered reader. Now, take a look at this code. The absolute key is this wrapping pattern. See how we create a regular unbuffered file reader, but then we immediately wrap it inside a buffered reader? That one simple step is where all the magic happens. So here's what's going on behind the scenes. First, we wrap that slow stream. Then the buffered reader goes and reads a big chunk of the file into its own internal memory buffer. Finally, when you call a method like readLine, it's just pulling that data from the super fast memory buffer, not from the slow disk. It's a huge performance win. Okay, so that takes care of reading. But what about writing? Well, the logic is almost identical. And for this, we've got the BufferedWriter. And yeah, this pattern should look really familiar by now. We create a standard file writer, and right away, we wrap it in a buffered writer. Now, whenever we call methods like write or newline, our program isn't hitting the disk every single time. Right, so here's the crucial point. The buffer text writer collects all your little write requests and holds onto them in its memory buffer. It waits until that buffer is full, or until you tell it you're done by closing it, and only then does it write everything to the disk in one big efficient batch. That's the secret to its speed. We've seen the how, so let's quickly sum up the payoff and then cover one absolutely critical rule that you just cannot forget. I mean, the benefits are pretty clear, right? You get much faster I/O, you drastically cut down on those slow system calls, and your whole program just becomes way more efficient, especially when dealing with large files. But, and this is a really big but, there is a catch. This is probably the most important thing to remember from this entire explainer. You absolutely must, and I mean must, remember to close the stream when you're finished. So why is this so critical? Because calling .close also flushes the buffer. It forces any data that's still just sitting in that memory buffer to actually get written to the file. If you forget to close it, that last chunk of data might never leave memory. Your file could be incomplete. You could literally lose data. All right, now it's your turn to really make this stick. Go ahead and pause this, open up your favorite editor, and try this quick challenge. Just use a buffered reader to read any text file you've got lying around and print each line out to the console. Seriously, it's the best way to let it sink in.
So if you take away just one thing, let it be this. Buffered streams are all about optimization. They minimize that slow, chatty, direct interaction with the file system by dealing with data in big, efficient chunks. It is a fundamental technique for writing high-performance Java code.
I really hope you found this useful. And hey, stick around because next time we're going to take this whole idea a step further and explore something even more powerful: object serialization. We're going to see how Java can take an entire object from your program and save its state to a file so it's ready to be loaded back in later. I'll see you then.